This is the 2001 Society for Assisted Reproductive Technology outcomes, and I don't think anybody here would have a difficult time at all selling this clinic. If you have a nearly 80% per embryo transfer pregnancy rate, people are flocking in your door. You don't have to worry about that. I'm going to show data today from a clinic I consulted with whose delivered pregnancy rate for under 35s is in the 35 to 40% per embryo transfer range. Candidly, this is a physician in California who runs a small practice and is dying on the vine. He may go into bankruptcy because in Northern California, you can find programs that have a 50 to a 65% delivered pregnancy rate, and the consumer is going to look at SART and know where you are. So only the ignorant or the lazy are going to wind up in this clinic, and those people are a non-renewable resource. There aren't enough of those. So quality winds up feeding back into our marketing program again. So the question we have is, what is our quality? What is our quality? We all try hard. We all do a good job. Some people have fabulous results. Most people have results which 25 years ago we'd just been happy to have, and some people do very poorly. If you're in this middle range, how do you know you're doing the best you can? How can you improve and give your marketing group something better to work with? What's interesting is from a perspective of effort, all of these clinics are making a good faith effort. Everybody's trying, everybody wants to do a good job, and yet the outcomes are very different. About 15 years ago, I was reading a book by Edwards Deming called The New Economics. And this is, at the time, a very revolutionary idea, taking thoughts that were used in manufacturing and applying them to education, governance, and corporations. I was struck by this comment. Even if you try hard, if you have an unstable process, your quality will be poor. Does this remind any of us who go back 25 years in IVF? We all tried very hard, but some people had the black magic. They had the right habits, the right ideas. No different in their effort, but they did the right thing. They had a stable process in good quality. Edwards Deming is an interesting man. He's part of a school of people who were in quality control in the 1930s. And he developed a system of profound knowledge that we're going to speak to aimed at the manufacturing process. Dr. Deming is the person who helped the Japanese kill the American auto industry in the 1970s by taking the principles we're going to discuss in a moment and applying them to manufacturing. An example of what came from this is Ford Motor Company in the mid-70s sold cars which either had American-made engines or Japanese-made engines. The Japanese engines worked far better. Clients wanted these. Well, the Ford engineers tore the engines apart trying to figure out what happened. The American-made parts were made to a spec, and all of them fell into spec. The Japanese-made parts were exactly on quality. They had, if it was supposed to be 10 millimeters, it was 10 millimeters, plus or minus a very small difference. Things fit together better, and they worked. So what Dr. Deming proposed is a system of profound knowledge, which includes appreciation for a system, an understanding of variation, which is to say, a way to track your system, a theory of knowledge, understanding what you can know and how you can apply that to a process, and psychology. And psychology of processes and their management is very important. In this morning's talk, we're going to hone in on systems and variation, although in our next talk, we're going to speak quite a bit about psychology and how you implement systems. What's a system? A system is an amalgamation of an idea of something that you want to do, design and redesign, assembling its parts, testing it, putting together the assembly process, making something, inspecting it, checking it for quality, and giving it to your customers. A stable process will have predictable high quality. That's what we all want, a stable process. In contrast, an unstable process will give good results sometimes, bad results others, inconsistent results, and ultimately poor quality. So the question that we have to ask in any walk of life, but what is very important to us as IVF practitioners, is your process stable? So let's look at this. Deming gives the example in the New Economics of a delivery van service. So here we have Acme Logistics. This is a graph of against time, on-time delivery. So this is the expected time. And the good people at Acme Delivery are a little early or a little late, but they're consistently right around their time. Every once in a while something bad happens. There's an auto accident, truck breaks down, they're late, but they have a consistent process and they're typically there. People at FedEx do it even better. They have logistics systems which are well thought out and well beyond anything that the people at Acme can. So again, they have good quality, they're very on time, they have an even less variation in their time. But even the folks at FedEx will run into the problem of a broken truck or an auto accident or something. Here's a local delivery system, and they're consistent, but their quality is less good. They're consistently late, but they're always in that same window. They have consistency but less quality. And then here's Pedro's delivery system. Pedro's delivery system, a couple kids working out of their father's garage, and they borrow trucks to take things around. They have very, very poor performance, and we can't ever know what's happening when they're going to be there. We're going to speak to the fact that the variation in the system here is common cause variation, and this is special cause variation. So let's look at this. Common causes of variation is variation inherent to your process. The quintessential example is if you have a drill press that is supposed to make a 1 millimeter hole, well, it might make a 1.01 or 1.0 or a 0.99 hole, but it's going to be consistent within that variation, which is the tolerances of the process. Compared to special cause variation, when the machine breaks and you make a hole that's 2 millimeters because you've lost control of it. Common causes are variations inherent to a process which are good. Special causes are problems which are outside the process that need to be corrected. So again, looking at this graph, we see common cause variation here, less of it here, special cause variation here. Let's explore this a little bit more. American currency has the logo, "In God We Trust." Dr. Deming riffed on this and said, "In God we trust, all others must bring data," which is to say, we need to know about the essence of our process and prove to ourselves mathematically that we have a stable process. This is the essence of process control analysis. So here is time on the x-axis and whatever value we're looking at on the y-axis. We have data points, which if you have a stable process, will accumulate over time and will be in a normal distribution. A control chart takes this information, and here's the mean, and you'll pick an upper control limit to say that as long as things are in the upper or lower control limit, that this is a stable process. Typically, this is 3 standard deviations. This way we know with 997 out of 1,000, if it's in this, it's normal, and If it's out of this, that's outside of the normal distribution. That's not chance. There's a problem. Here's an example of a skew-heart control chart of a in-control process where all the measurements stay within the upper and the lower control limits. In comparison, here's an out-of-control process with many of the data points being outside the upper and lower control limits. This is an out-of-control process, and these are being caused by special causes of variation. So again, common cause variation this is interesting mathematics. We are so accustomed to using the normal distribution to prove that things are different. Here we're going to use the normal distribution to prove that things are consistent within a process. So common cause variation is variation up and down, falling within a normal range due to the inherent limitations of your process. Special cause variation, again now, is outside of your control limits, often 3 standard deviations, and this is due to an assignable cause. In addition to special causes of variation being points outside this, there are other patterns which are important. The fact that we have a normal distribution implies that values are going to cluster around the mean, 50% above, 50% below. When you have patterns which becomes outside of that, that suggests, again, a special cause of variation. Here's an example of a cyclic problem. David Hill, who runs ART Reproductive in Los Angeles, tells the story of using air handlers that were supposed to be changed out according to the manufacturer's recommendation at 4 monthly intervals. He wasn't happy with his results at times and was advised to cut open his permanganate filters at 1 month, 2 months, and 3 months. And sure enough, by 2 months, the permanganate filters were saturated, and he might have had a situation where he had good results, and then as the filters saturated, poor quality, they change the filters and they get good quality again. Cyclic pattern. A downward shift pattern might be a new technician. For instance, look at fertilization rates. You hire a new technician or teach somebody how to do ICSI, all of a sudden the fertilization rates go down. A systematic problem is often when you see these wide fluctuations, multiple inputs of instability causing wide variations in the pattern. Interestingly, they stay within the upper and lower control limits, but there's wide variation. And then this is a poor drawing, but it gives us the idea that if this is our median and this is about 1 standard deviation, most of our points are going to coalesce here. An unstable process has points out towards the control limits, even if they're not exceeding it. So Skewhart, who is really the father of process control analysis, taught us that to bring a process into statistical control within the control limits we've seen, where there's only common cause variation is what's needed to have an effective process. So if we're going to use process control to improve a process, we begin by charting, seeing that there is a out-of-control process, and then taking interventions to, first of all, bring the process into control. Then if this is our specification, if this is our requirement, improving the process so that we get towards spec and eventually even better in control. And the method that Deming proposed is the PDA cycle: assess a problem, plan an experiment, implement, conduct the experiment, collect the data, analyze, interpret, improve your quality, and do that in cycles and cycles to reduce variation and improve quality. Well, if you can do this with a logistics company, you can do it in IVF. We haven't, but we should. Let's come back to the SART numbers again. Everybody's making a maximal effort, yet the results are different. So the question we wanted to ask is, does process stability contribute to our success? Can we define this? So to do this, we use the Artisan EMR system to collect granular embryology data. Here's a case where a patient had 13 eggs, a pretty good fertilization rate, nice day 3 embryos, and very nice quality day 5 embryos. So we've analyzed this, and we did something similar to what Dr. Edwards did years ago. We said, okay, embryos are best quality, worst quality, or intermediate, 4 cells to 10 cells, and we assigned embryos in this block, just empirically, as grade A, and we'll give them 6 points. Intermediate quality embryos we'll say are grade B, and these poor embryos, which have a very low likelihood of making a pregnancy, are grade C. We'll give them an embryo score by multiplying the number of cells by the grade. So this 9-cell number 1 embryo is 54 points. A 5-cell embryo here is 15 points. Any embryo in the red, of course, is 0 points. So let's look at a couple of examples of what comes from this. Again, here's this very nice case with very nice day 3 embryos, very nice day 5 embryos. The majority of the embryos, both on day 3 and on day 5, are in the upper right-hand corner of the grid. The mean embryo score for this case is 52 on day 3, and it's consistently 52 on day 5, and the percent of high-quality embryos for this patient was 100%. This is a good case. In comparison, here's another case in the same laboratory in the same month. Good numbers of eggs, pretty good fertilization. We start to see more embryo fragmentation, irregularities, and lowered cell division on day 3 here, and only 2 embryos went past cleavage stage out of the bunch. As you'd expect, we see that the embryos are now coalescing in the lower left-hand corner of the grids. The day 3 mean embryo score was 16, and about a third of the embryos were high quality. By day 5, there was next to nothing that was good. So we can obviously critique an individual case and see whether or not we have good embryos or bad embryos. The question is, can we distinguish between clinics? I'm going to move much faster now because I see I've taken too much time. Here's 2 clinics. Both are small practitioners, people aged under 35. Clinic A is a high throughput clinic. This is actually Dr. David Meldrum's laboratory in Los Angeles, well-known, high pregnancy rates. These success rates are top 10 percentile in the country. This is a small clinic, again, about 80 cases, single practitioner, 40th percentile results. This clinic uses an itinerant laboratory director, and we can look at the way that we've set up the mean embryo scores from a range of 0 to 60. And the 3 standard deviation lines actually fall outside of the range because there's so much patient variation. But if we go to showing a 1 standard deviation, this will give us an idea of things. Here's Clinic A, which is a nice in-control process. Most of the mean embryo scores on day 3 cluster around a nice mean. They're around, most of the scores are close to the mean. There's very little variation outside. Here's Clinic B, and you can see with the naked eye that this is a different outcome. There's much more variation in this compared to this. Let's look at it closely, and we're going to see that there's evidence of special cause variation. First of all, compared to Clinic A, it's not performing nearly as well. Most of the values are outside the 1 standard deviation overlay of Clinic A, and we have groups of time points here where there's special cause variation, where almost everything is below the line, indicating that this is something out of statistical control. So clearly we can tell that, and here's a point where we see lots of high variation, again, special cause variation. But people say, well, it's not fair to compare because my patients are harder than yours. So what we do is we normalize the patients, we compare idealized patients. Here's Clinic A again with its idealized patients. Again, we see wonderful statistical control here. And the 1 standard deviation line is even tighter once we get rid of the patients who are only less age 35 and a good egg retrieval. We see again the high amount of variation in day 3 mean embryo scores, even in these ideal patients in Clinic B. There's clearly a problem here. So the question is, can we figure out where that problem is? And the answer is yes, we can do that very nicely. Here is the number of eggs retrieved, and these are very, very similar. clinic B even gets a few more eggs, we see a nice in-control process in each of these graphs. When we get to percent fertilization, not surprising, not that much difference. Again, there's a little variation in clinic A, which surprised me when we did these data, a similar amount of variation in clinic B. But when we get to day 3 marks, we see a big difference. And here are the ideal patients in day 3, very, very close to the mean. And here is massive variation in clinic B. So what we can take, and then additionally, if we look at the percentage of high quality embryos, we see the same variation. So what we take from this is that in clinic A is in tight statistical control and is high quality. Clinic B, on the other hand, has a loosely controlled process, evidence of special cause variation, and very poor quality. How can we use process control in our clinical art practice? We can begin by using the PDAC cycle, assess, work ourselves down this graph, and improve the quality of a process. That's a global thing which you can do at the beginning of this application. After that, there are other uses of this, beginning with staff education and monitoring. We want to know that, for instance, as we bring on a new technician, are they performing according to standard? We can look at ongoing quality assessment to be sure that as we change our processes, that we're not getting a decrement in our quality and in our consistency. And then, I don't have time to speak to this now, but there are real opportunities for research, changing the way in which we do large-scale research in the groups that we compare. What's next? In our current investigations, we're working with the SART database, looking at variability in sequential aspects of the IVF process across a number of clinics clustered in success rates. We'd like to see what is the natural history of variation as segregated by quality. Another database that we have is a single center. Over 10 years, we have really granular data on over 10,000 patients, and we're going to look at the impact of physicians, lab techs, changes in environment on quality and consistency. Lastly, we are opening a study now in conjunction with one of the major pharma companies in America, where we're providing the EMR software that we've showed you to 40 to 50 clinics and looking at their process variation. And we'd like to open this collaboration and find another 40 to 50 clinics worldwide to be able to look at the value of process control, first of all, in identifying the quality of your process, and then secondly, improving the quality of the entire IVF process. It's time for me to say thank you for your attention. I want to give due respect to my colleagues, Dr. John Pan, and my graduate student, Eric Friedman, at the University of California, San Luis Obispo's engineering department, whose work in process control has been very helpful. Thank you for your attention.